Hi, folks. In this lecture, we're going to be finishing up our discussion on hypothesis testing, and we're going to move right into t-testing. So this will be a little bit different than some of the previous lectures. We'll start with some theory, but we're going to spend a lot of time on some applied examples using the one sample t-test. Specifically, in this lecture, we're going to talk about type 1 and type 2 errors, statistical power, statistical significance versus the effect size. And then we're going to put it all together with that one sample t-test example that I described earlier. Conceptually, type 1 and type 2 errors are pretty simple. Type 1 error is the error you make if you accept your research hypothesis as being the most plausible hypothesis for your data when the null hypothesis was actually true. So in the case of a t-test, I would accept my research hypothesis that there is some difference perhaps between the sample that I have and some theoretical population, when in actuality, those groups aren't really different. Typically, this is the kind of error that we're most concerned with when we're doing hypothesis testing. Type 2 error, on the other hand, is the error that you make if you accept the null hypothesis when your research hypothesis was actually correct. So in this case, I'd be looking at my sample and I would say that my sample actually comes from the theoretical population that I'm referencing, when in actuality, that sample is from a different population. Statistical power is actually related to type 1 and type 2 error. Statistical power is the ability to detect that your research hypothesis is true if the research hypothesis is true. It can be affected by a number of different things. One of the things that it's affected by is the size of the effect that you predict exists between your reference population and your sample population, your focal population. It can also be affected by the size of the sample that you're using. I think the next couple slides are very important when it comes to discussing statistics. We use the term significance in common conversation to mean that something's important, so that something really matters. A significant event in your life is an event that really changed the course of your life or really mattered for you for the rest of your life. But statistical significance doesn't mean that. What statistical significance means is that we are relatively confident that whatever thing we thought is causing an effect is actually causing that effect. It could be that we're relatively confident that there's a difference between groups, say groups that are taking different therapies to manage a particular mental illness. It could mean that we are pretty confident that there is a relationship among variables. For instance, that the amount of exercise one does is important in managing one's stress. So the amount of time spent exercising is related to the amount of stress an individual might feel. But if we find a statistically significant relationship, all we're saying is that we're pretty confident a relationship exists. What we commonly refer to as significance equates better to effect size in statistics than it does to statistical significance. You see, statistical significance just means that we're sure that there is some sort of effect or relationship, but that effect or that relationship may or may not really be an important one. Effect size, on the other end, tells us how important or how strong some particular treatment is as it relates to some particular outcome or another variable. So effect size is the closest analog we have in statistics to the common term significance, or how we use the term significance commonly. Okay, I know this may have felt like a bit of a speed run through the underlying theory, but I'd like for us to really sort of wrestle with this or really think about it as we work through an example. So we're going to try to put this all together as we go through an exercise of testing a research question. And so we're going to start with the question, do productive people spend less time on their phones than the average person? You may remember from the last lecture that the formal procedure for hypothesis testing has 5 steps. We're going to walk through all of those steps here, but I just want to remind you of what those steps are. First, we're going to restate our question as a pair of hypotheses, the research hypothesis and the null hypothesis. After we do that, we're going to determine the characteristics of the comparison distribution. What are we actually comparing our sample to? And then after that, we'll determine the critical values for that comparison distribution. But remember, we could also simply set an alpha level if we are using some software or if we're going to do the math of calculating the p-value associated with our data. After we've identified those critical values and set our alpha, we're going to go ahead and we're going to calculate our statistic. And again, if we're willing to do the math, able to do the math, or if we are using the assistance of some program that will do the math for us, we'll also get our p-value. After we have those things, we need to make a decision, and we're either going to decide to accept our research hypothesis or reject our research hypothesis and accept our null hypothesis. So let's put this to work here. So we need to restate our research question as a paired hypothesis. Our research question is, do productive people have less screen time on their phones than average people? And we can break that into paired hypotheses that would look something like this. Our research hypothesis might be that productive people actually spend less time or have less screen time than the average person. You can think of it as the screen time for productive individuals is less than the screen time for the average individual. Alternatively, we could have our null hypothesis then be the complement, and that would be that productive people do not have less time on their screens than the average person. So in this case, the screen time for the productive person would be greater than or equal to the screen time for the average person. Next, we have to determine the characteristics of that comparison distribution. And really, we're just asking, what are we comparing our sample to, right? And so if we're interested in understanding whether or not productive people have a different screen time than the average person, which is a theoretical population, right? I don't really know what the average person does, but I'm going to work with an estimate of that theoretical population, right? So the distribution of screen time for the general population is our comparison distribution. And just for the purposes of this example, I'm going to do a little magic, and magically we will know that the mean is 5.74, and that's in terms of hours on the screen, and the standard deviation is 0.387. Again, that's in hours time on the screen per day. Now, the distribution for screen time for productive people in our example here is going to have a mean of 5.53 and a standard deviation of 0.729. Also, and this will be important later, we're going to use a sample of 20 individuals, which means that we'll have 19 degrees of freedom. Degrees of freedom aren't something that I've discussed too much explicitly, so I'm just going to briefly define degrees of freedom as the number of values that I would have to give you before you could know for certain what the remaining values are, all right? And so in the case of a population where I know the mean, well, if I know all but one of those values and I know the mean, I can do a little bit of algebra to figure out what the remaining value is. The next thing we have to do in our formal process for testing hypotheses is we need to determine what the critical values or alpha will be. And as we are getting ready to do our analysis. So we're going to have to state our alpha no matter what. And as a reminder, alpha is the amount of error that we are willing to accept as we make a decision to accept our research hypothesis. In other words, I'm willing to accept, in this case, that 5% of the time, if I did this analysis 100 times, I'm willing to accept that at least 5 of those 100 times, I'm probably going to incorrectly accept my research hypothesis and reject my null hypothesis. That's what I'm willing to tolerate. And so we're going to keep that same alpha value here. There's nothing magic about the number 5%. It is entirely arbitrary. You could consider it to be an ethical and moral decision or a functional decision, depending on what needs to be done. But this is not a magic number. If I can accept, however, a type 1 error rate of 5%, or my alpha then is 0.05, that means if we take a look at a table of the t distribution values, I have a one-tailed hypothesis because I'm saying that my sample has a lower screen time value than my reference population. And since I have a one-tailed hypothesis and a 5% type 1 error rate, or 0.05 alpha, if I'm using a one-sample t-test, then that means that my critical values would be negative 1.729. And this is actually only going to be one critical value because this is a one-tailed test. If this were a two-tailed test, that alpha of 0.05 would be split between both sides of the distribution. So I would have 0.025 on one end of the distribution and 0.025 on the other. And then I would have two critical values associated with those alpha values. But since we have a one-tailed hypothesis, all of my alpha is going to be on the left side of the distribution here because I'm saying that my focal population has a lower mean. It'll be on the left side. If I was saying it had a higher mean, it would be on the right side, right? And my critical value, again, will be negative 1.729. Now, we're actually going to calculate our statistic. In the previous lecture, I sort of gave you a general idea of how a t-statistic is calculated. It is generally similar to the calculation of a z-statistic, but there are some slight differences. To calculate the t statistic for a one-sample t-test, I'm going to take a look at the difference between the mean of my sample, or x with the little bar over the top. You'll hear me call that x bar moving forward. I'll look at the difference between x bar and mu, which is my theoretical population mean. And then I'm going to divide that difference by the standard deviation of my sample. That is also divided by the square root of my sample size. Right? You'll hear this term referred to as a standard error, depending on which text you might read. But there's only a handful of values I need. I need to know the mean of my sample, the mean of the reference population, and I need to know the standard deviation of my sample and the sample size. After I do the arithmetic, I'll have a t-statistic. And let's just go ahead and plug in some values here. So the mean of my sample was 5.53. The mean of the population was 5.74. I'm going to divide that by 0.72 divided by the square root of 20, or my standard deviation for the sample divided by the square root of my sample size. And I'm going to wind up with a value of negative 1.288. Right? This is my calculated t that I need to then compare with the critical value, and we'll do that next. So to compare that calculated statistic with the critical value, it is a straightforward comparison. Negative 1.288 is not less than or equal to our critical value. So it is not as extreme or more extreme than our critical value. And therefore, we have to reject our research hypothesis and we must accept our null hypothesis. There is no, or rather, our null hypothesis in this case is that our productive folks do not spend less time on their phones than the average person. And that's it. Those are the steps we walk through to do a one sample t-test from data from a sample and a theoretical mean. And we can take that and we can make a decision about whether or not we believe that that sample comes from the same population that the theoretical mean came from. So the calculation is pretty straightforward and relatively simple. And to be honest, it gets even simpler when you're doing it in SPSS. I'm not going to do this in SPSS for this lecture, but for the next lectures, we will be working in SPSS, and I will show you some examples of calculating multiple types of t-tests in SPSS. There are, however, a few things that I still want to clarify about these numbers that we calculated and these concepts that I kind of moved through relatively quickly earlier on in the lecture. So let's talk a little bit more about statistical significance, effect size, and power, and their relationship. Okay, so in our example, we had a critical t-value of negative 1.729, and our calculated t-value was not less than that. It was not more extreme than that. And so we had to reject our null hypothesis. There was no statistical significance. But what could have given us a statistically significant result? Well, if you take a look at the equation that we have to calculate our t-statistic, you can see there's actually lots of ways that we could do this. One that is probably what most people would think statistical significance means is that there's a bigger difference between our sample mean and the mean we're comparing it to, right? That's kind of what we typically think about when we are saying that there's a statistically significant difference between means, that they are further apart, right? And so yes, if our sample mean was smaller, if our sample mean was 4.97, and we had everything else the same, and we ran our calculations, we would find a t-value of negative 4.724. Now, there was no magical reason that I chose 4.97. I just chose it, and it happened to be a number that worked because it was sufficiently small. But a difference between the means that we're comparing is not the only way that we can have a statistically significant result. And this is important. This is part of the reason that it's important for you to think about effect size and not just statistical significance. For example, if we have the same sample and population means, and even the same standard deviation for our sample, but we had a larger sample size, so we've collected more data points that had the same mean, we could run our calculations again, and we would also find that the difference is statistically significant. If the sample is large enough, in other words, it magnifies the value of the difference between the two means. And this, if you think about it, makes more sense if you think about statistical significance as how confident we are that there's a difference between our means in this case. Remember what we talked about samples versus populations. I explained that samples are a subset of the population. And the closer the size of the sample gets to including the entire population, the more accurate any estimates of this population size are when we make them from the sample, right? If I have a bigger slice of the population of humans, and I'm trying to understand on average how tall humans are, well, the bigger my sample is, the closer it's going to be to the population, which is actually the largest sample you can take, right? And so this sort of makes sense. If our population gets bigger, I am more confident about what my sample mean is. And since I'm comparing it to a theoretical mean that I'm certain of, if I can be very confident that my sample of what my sample mean is, then I don't need to see as big of a difference between the sample mean and the comparison before I'm willing to say that they are actually coming from two different areas. If that doesn't make sense, of course, I'm going to encourage you to think about it a little bit longer, but please feel free to set up some office hours with me sometime soon. I'm happy to talk about this more because I understand that this can be a little confusing. I'm going to point out that a large sample is not the only way that we could be confident that there's a difference between our groups, or find statistical significance, in other words. Again, if we think about what these statistics mean, then we should consider the standard deviation as well. If you recall, the standard deviation can be thought of as a measurement of how good the mean is at estimating the population, right? The standard deviation is effectively the average distance of each observation from that mean. And so the smaller the standard deviation is, the more accurately the mean represents the population. So if we have a smaller sample size, a smaller standard deviation with the same values everywhere else, we could also find statistical significance, all right? So recall and remember, please, that statistical significance does not mean that there is a big difference between the means in this case. What it means is that we are confident that our sample mean is different from our population mean. Okay, so effect size is some measure of how important the difference is, or how important the factor is that makes the difference between two groups, or in some cases it's a measure of how strong the relationship is between two variables. For this lecture, I'm going to talk about effect size for z and t-test. In those cases, since the z-test and the t-test are comparing means of groups, the effect size is really giving you some sort of standardized difference between the means that you're comparing. The formula on the left on your screen is a calculation of effect size if we were using a z-test. Now, a z-test is an appropriate test if we know the population mean and the population standard deviation, and we want to know if some sample belongs to that population. It's very rare that we would know the population standard deviation, and so if you don't know the population standard deviation, you could use a t-test, like what we did in this example. Ours was a one sample t-test. At any rate, if you're using a z-test or some type of t-test, Cohen's d is a measure of effect size that we can calculate. It does pretty well if we have samples that are larger than 50 observations. For samples that are smaller than that, there are other measures of effect size that we can calculate. You can look at these formulas here and see that with Cohen's d, we are clearly measuring how many standard deviations apart our comparison means are. Now, as you are measuring different types of t-tests, as we will deal with in the next two lectures, if you're using different types of t-tests, the standard deviation that you use will differ depending on the t-test that you're doing. But for our one sample t-test, it is what you see on the right side of your screen. Cohen's d is the difference between the sample mean and the population mean divided by the sample standard deviations. In other words, how many sample standard deviations apart is the sample mean from the population mean? The larger this value is, the greater the effect, or greater the effect size. Now, that can be a direct relationship or a positive relationship, or it can be an inverse or negative relationship. The things that effect size is affected by are the size of the difference in populations and the size of the standard deviation. The larger the difference between populations, the larger the effect size, and the smaller the standard deviation, the larger the effect size. Okay, so our statistical power is related to our type 2 error. Remember, type 1 error is the likelihood that we will incorrectly reject our null hypothesis and accept our alternative or research hypothesis. And type 2 error, or beta, is the likelihood that we will incorrectly accept the null hypothesis. So what this means, if we could just picture these two hypothetical populations that are pictured here, on the left in sort of gray, we have this population that we're saying the data might come from. This is our null hypothesis population. In our example from earlier, this is the population that has mu as its mean. On the right, however, is the population that our data actually came from. Now, there's some overlap between those populations, and the job of statistics is to figure out whether these data in the overlap actually belong to a population that encompasses both of those two bumps in your figure, or if those data belong to the bump on the right, right? So if we're just sort of picturing how this error works, our type 2 error is when we're looking at those data and the overlap between those two populations. And those data really do come from the population on the right, but we mistakenly assign them to our null hypothesis. Right? And so I hope this sort of helps you visualize this. We'll talk about this a little bit more later, but I want you to kind of keep that picture in mind if we're thinking about where our statistical power is. And that, again, our statistical power is the ability to correctly assign those values to the population in the green. Mathematically, it's related to the error in that power is 1 minus our type 2 error, or 1 minus beta. Okay, that's it for this lecture. Next up, we're going to be talking about t-tests. So we'll start with the one sample t-test, which we sort of walk through an example of in this lecture. And then we'll get into other types of t-tests. So two sample t-tests, where we are either comparing data that are independent from one another, samples that are independent from one another, or samples that are related to one another. And that will be with or without equal variances. And then we'll talk a little bit about non-parametric alternatives to the t-test. After we've gone through all of this information on t-tests and some examples, that'll be it for the course. So between now and the end of the course, I trust that you will reach out with any questions that you have about the topics that we've covered. So I want you to have these basics down packed before you move on to your next course in statistics. Take care.